webinar. Today's speaker is, we are very happy to have Shuntaro Aoki from Chung-Ang University. He'll talk about the continuous spectrum on cosmological collider. Please start when you're ready.
Thank you for introduction. Thank you for having me. I'm Shuntaro Aoki. Maybe you already know about me much. And I'm from Chung University. And from September 1st, I will move to IBS. So today, I'm going to talk about this topic, which is the continuous spectrum of cosmological collider. And also, I want to, this talk is based on that paper. And also, I want to introduce another ongoing work with these Japanese guys. So, move. Sorry, it doesn't work. Okay, thank you. I think you guys are familiar with this kind of topic, but this is the one slide introduction for the inflation. So as you know, inflation is a rapid expansion of the early universe, and also it is very theoretically established because it can solve some initial conditions of the standard Big Bang cosmology, like horizon and flatless problems. And also, it's not necessarily, but in some inflation models, it can be a source of the primordial fluctuation. And I will talk about this point in detail in the later. And actually, there are many kinds of inflation models, but the most easiest one is to use a single scalar field called the inflaton. So this figure shows the inflaton potential. So in the early stage of the universe, because of this potential energy of the inflaton, we can experience the rapid expansion because this height corresponds to the energy of the inflation, and this can be source for the expansion of the universe. So at this stage, the inflaton is slowly rolling, and at some point, the inflation ends and start oscillating, and it's continue to the heating error and subsequently continue to the Big Bang standard cosmology. So actually, this inflaton is quantized, and this quantum fluctuation is converted to the curvature perturbation. So we can observe from the CMB observation, we can have information of the curvature perturbation, and it turns out we can restrict the potential or some inflaton dynamics. So this is a pictorial slide for the inflationary observable. As I mentioned, the curvature perturbation, we have a curvature perturbation may be sourced by the inflaton fluctuation, and we can observe some correlation function of the curvature perturbation. And also, this is not today's topic, but the inflation also predicts some tensor perturbation, so we can also observe the correlation function of the tensor perturbation. So main target is a two-point correlation function called the scalar power spectrum, which is a two-point correlation function of the curvature perturbation. And also you can define the similar quantity for the tensor perturbation. That is called the tensor power spectrum. And sometimes we are interested in the tilt. That is the momentum dependence of this quantity defined by this equation. And also, as you know very well, this kind of scalar tilt, and also this is the ratio of the tensor power spectrum and the scalar one, they are restricted by the observation. Actually, if you assume the single slow roll inflation, these quantities are related by the derivative of the inflaton potential. So from the observation, you can restrict the inflaton potential, the form of the inflaton potential. And as you know very well, this is the Planck result. And some of the models, the simple model like a chaotic inflation are excluded. And for example, the Starobinsky type, like R-square inflation is favored by the observation. So this is the standard story of the inflation. But today I want to talk about more higher point correlation function. For example, you can go beyond the 2-point correlation function, like this is a 3-point correlation function, and this is a 4-point correlation function. And also, I will not talk about today, but you can also consider the singular quantity for the tensor perturbation. So the more precisely, the picture is like this. This is the time direction, and this is the CMB surface. At some point, I assume the self-interaction of the inflaton. So because of this self-interaction, the curvature perturbation is created, and I'm sorry, and it leads to the some imprint on the 3-point correlation function. So this is called gravitational flow because this is coming from the inflaton self-interaction. So if you assume the very simple setup like Einstein gravity plus inflaton, you can always have this kind of interaction. So this is kind of how to say the minimal contribution to the 3-point correlation function. And also the Mardasena shows, yes, he starts from the general setup from Einstein gravity plus inflaton single slow inflaton setup, and he showed this 3-point correlation function. I use FNL. This is a kind of a magnitude of the 3-point correlation function, but he showed this is very small. With epsilon is a slow parameter like a 0.01 during inflation. And the assumption is that here he assumed a single scalars and also Einstein gravity and also canonical kinetic term for the inflaton and the slow inflation. And I missed one more condition. He assumed the Bunch-Davies condition. But under this condition, this result is quite generic. Yeah, please.
Oh. I mean, maybe it's a very nice question. What do you mean these correlations are coming from, say, down?
So inflaton has the kinetic term and the potential term, right? Which couple to graviton. And we expand the inflaton around the inflaton background, time-dependent inflaton background. So you can write down every interaction for the inflaton. And it's this kind of cubic interaction is contained. So you can calculate from the inflaton cubic term to the correlation function of the inflaton, and which is converted to the curvature perturbation.
Potentially, if there is no phi cube term, then this correlation will not be there. Like
Sorry?
phi cube or phi 4 term. So if I simply write m square v square, then we will not get this correlation.
You mean just a phi square? Yes, but the phi square is it's a chaotic impression, right? I don't consider that scenario because it's already excluded. But in general, assume the generic function of the inflaton, you can expand, and it's this kind of interaction is complete.
But what kind of non-canonical kinetic terms can you
This contains
to avoid this?
For example, if you go beyond the, how to say, like a higher derivative kinetic term, or like maybe the famous example is a kind of dBi inflation. It is contained like a square root inside the kinetic term, something like that. In that case, this discussion doesn't apply. So this assumes just a canonical, like a del phi square, but if you go beyond, this assumption is violated. And also, yeah, this is related to your question. If you violated one of the assumptions, you may have a chance to get a large non-Gaussianity. I mean, non-Gaussianity means a kind of magnitude of the 3-point relation function. You can get a large non-Gaussianity from more general classical inflation. If you consider, for example, multi-field inflation or higher derivative inflation with a higher derivative, you have a chance. So the last comment is Yeah, of course, there are very well-known famous relation between the n-point correlation function and the n+1 point correlation function, like soft pi and theorem. In this case, by using these relations, we can distinguish the inflation models. For example, let me explain this bound, Yamaguchi bound. This is a kind of inequality, and the equality only holds to the single inflation models. But if you have merge field, in general, this equality is violated. So this kind of relation can be used to distinguish the inflation models. So what I wanted to say is the higher point correlation function or non-Gaussianity have a strong restriction on the inflation models. But today I want to talk more about the non-Gaussianity that is called the cosmological collider law. So the picture is like this. The same figure, I consider 3-point correlation function again. But I assume at the early universe, some heavy field sigma is created, and it can decay to the inflaton fluctuation in this way. So in this case, as we will see later, this 3-point correlation function or non-Gaussianity can contain the many information of this heavy particle sigma with a specific oscillation signal. Actually, in the momentum space, you can analyze the structure of the 3-point correlation function, and you can find we get some oscillation signal as a function of the momentum. And it turns out this oscillation frequency is proportional to the mass of this new particle. So from this oscillation behavior, you can read off some information of this signal. And also the important point is this sigma particle can be heavy, like the mass of the sigma can be as large as the Hubble scale during the inflation. Of course, it depends on the inflation models, but at the maximum, it can be a 10 to 13 GeV, and this energy scale is much larger than the energy scale on the ground. So we can explore very high energy. And also, as I said, Mardasana shows the non-Gaussianity from the self-interaction is quite small, which is proportional to the Schroeder parameter. But depending on the diagram, this signal can be large. So it gives a dominant contribution beside the gravitational flow. So my conclusion is the cosmological collider can give a new tool for searching a high energy. This is a kind of introduction. Actually, so far, there are many works. For example, this paper considering the setup to search a supersymmetry theory by using cosmological collider. And also these guys exhausted some inflaton sigma interaction based on the EFT approach. And also people discussed the spinning particle. In the previous slide, I assumed the sigma is a scalar field, but you can consider some spinning particle mediation, and you can read off the information of the spin from the cosmological collider. And also, yeah, this is Shiro Kim. He's a group of this. He's a member of this group. He's working on this kind of topic. And also, there are many other applications to the DSM.
If your spinning particle means the spin up to how large is the spin is?
Actually, the first paper is quite general. They consider higher spin particle, but I remember it is integer spin. Integer spin. Half integer maybe it's contributed to non-Gaussianity at the loop level. Like maybe you can imagine fermion situation. In that case, the analysis becomes more complicated.
So one can introduce like only one such sigma field, or there can be something new.
So I don't get you.
So I'm saying that only one sigma field can be introduced to realize?
Okay, that's a good point. In general, it is natural to have a many fields whose masses are around Hubble scale. So in general, they contribute at the same time, and we get kind of superposition of these. Actually, it's related to my later talk. So I want to come back to this question. So the question is, can we really distinguish the BSM from this kind of technique? Actually, my personal view is still far from the practical application. Of course, thanks to the previous work, we know many features for the cosmological collider, but still there are many technical problems. Actually, this is a technical point, but in our case, the vertex has the coupling has a time independence. So we need to perform a time integration to get non-Gaussianity. But in general, the mode function of the sigma particle is quite complicated using the a special function. And practically, it is very hard to perform such a time integration. And also, if you go to apply, if you want to apply this technique to the fermion, for example, you need to evaluate the loop diagram. But this is quite difficult. And also, recently, there are many developments in the so-called cosmological bootstrap program. And this is, how to say, this argument is based on the symmetry. Without doing this kind of time integral, how to get a final result. I think this is one of the way to avoid the difficulty and to get the final result, but I think it's still in development. So this is kind of my personal. So, however, even at this stage, as I said, it's still far from achieving the to distinguish the BSM. But however, at this stage, there are some models that predict distinctly different signals that are distinguishable from the others. And this gonna be the my today's topic. That is one is the continuous spectrum on the CC, a cosmological collider, and also effect of the time-dependent mass to the cosmological. Okay. So I think it's related to the previous question. Actually, before going to the continuous spectrum, I want to talk about the large field effect on the cosmological collider. As I mentioned, in the realistic situation, I mean in the realistic BSM setting, natural setup is we have many multiple heavy states whose mass are around the Hubble scale. So picture is like this. During inflation, only the inflaton is light, like a 10% times the Hubble scale. And around the Hubble scale, we have many heavy particles. So example is the supersymmetric theory. In this case, we have a super pattern of the standard model. And this get soft mass because of the supersymmetric breaking. And this breaking scale is characterized by the Hubble scale. So we naively expect the particle has the mass around the Hubble scale. So you can easily get this kind of situation in the supersymmetric theory. So another example is the extra dimension. As you know, extra dimension predict the infinite tower of the KK mode. So you get many, actually infinite tower of the KK mass appears. And one unclear point is that they have a mass around the Hubble scale. And at this point, it may be model dependent. But anyway, I want to say the existence of the large field state are quite general.
What is the root delta?
Root theta is one of the slow parameter. So like root theta is like 0.1 or something.
Utilitarianism.
Yeah, something like that. Yeah. And also, you can easily find that even if there are several heavy particles around the Hubble scale, but the whole signal is governed by the lightest particle. Because this is because of the Boltzmann suppression factor. The non-Gaussianity or correlation function generally contain this kind of Boltzmann suppression factor. So even if you have some stack of the field, the lightest particle dominantly gives the signal of the non-Gaussianity. And also, exception is we have the case with the degenerate mass. In this case, the degenerate particles collectively affect the non-Gaussianity, and you can expect some superposition or beating effect of the wave. So I also worked on this direction in the previous work. But the conclusion is just this. What I want to say is this. The lightest particle affect the signal. So today, as I mentioned, I want to consider some continuous spectrum, which is a kind of extreme situation in the multi-field situation. So this is the figure explains what I meant. Discrete situation, the lightest particle affect this orange one dominantly determine the signal. But I want to ask is if the continuous situation, maybe certain region around the Hubble scale collectively affect the signal, and maybe we can expect some non-trivial signal in this case. And actually, this is the maybe point we need to discuss. Actually, when I wrote the paper, I'm not so serious about the UV embedding of this continuous spectral scenario. But recently, I found a paper by Kuma and Sandram, and they tell us some setup for the. Actually, according to this paper, we get continuous spectrum, and whose mass lie around the Hubble scale. And the situation is like this. They consider the RS-like setup. So it's a non-compact, and there's one brane. And the inflaton is confined on this brane. And the graviton is on the bulk. But as in the same way as the RS2 scenario, the graviton has a bound state, which is massless. And we have a continuous spectrum around some point. Actually, in the original model, we have a massless graviton. And from zero, we have an infinite tower of the continuous spectrum. But in this scenario, they prepare some energy for the brane. Actually, this is coming from the inflaton energy, potential energy. Then, in that case, they show the graviton mass spectrum, I mean the KK graviton, starting from this value, the continuous spectrum starting from this value. So
you mean really continuous, not like some rational number.
In this case, the continuous spectrum, but actually they focus on the discrete spectrum in this paper, and they prepare another brane here, and also they introduce some additional field to stabilize this radius. So the situation is more complicated, and in that case, they get a discrete spectrum, and they are checking some effect of the lowest lightest particle effect. But if you do not introduce another brane, and you can find from this paper this kind of spectrum.
When you say continuous spectrum, many tower of particles with almost degenerate mass.
Actually, in this situation, actually, even if you have another brane, you can take a limit. This brane goes to infinity. In this case, this spectrum is exactly continuous at that limit. So in this case, the interval becomes 0. Yeah. So this may give a example for the continuous spectrum from the extra dimension. And in this case, they focus on the effect of the graviton. But in my case, I want to simplify. So instead of the graviton, I prepare a single scalar field. And I assume this has a continuous spectrum and which coupled to the inflaton. Actually, we can take.
I think that here, what do you assume for the functional form of when scale is some power or whatever?
Yeah, actually, I will show you later. But I changed some functional form. So I tried.
Is it predictable, theoretically predictable, or not within this setup of syndrome and?
Actually, relation to this setup is not clear. But I read another paper. They use a continuous. I think it's a Korean guy. They use a continuous spectrum.
Oh, you mean
for the-
Sung-Jae Lee?
Yeah, right. For the dark matter
Oh, yeah,
application.
okay.
Then the model setup is totally different from this, but I used their spectral density for this analysis. And also I changed some functional form of the spectral density, but I didn't see many difference, so maybe conclusion doesn't change much.
Anyway, it's a positive power of some m to the some positive power, not exponential growth.
Not exponential, right? I didn't check what happened if the exponential. So see.
I mean, they completely kill the this Boltzmann separation factor, like Hagedorn temperature in thermodynamics.
Okay. If maybe if exponential, I don't know such exponential type is
polynomial,
mostly
basically you are assuming polynomial type.
polynomial type, exactly, yeah. So yeah, this is the spectral density which characterize how the spectrum is distributed. And of course, you can, if you take a delta function like, you get a discrete or single particle spectrum. But in general, this can be a function of the mass, which start from some scale that is called mass gap. In our case, this M0 should be half scale. From this point, I forget the extra dimensional setup. Just to see to catch a feature, I assume the coupling between inflaton to the sigma field in this way. So sigma coupled to the inflaton kinetic term in this way, and the potential is separable just for simplicity. And as I mentioned, the pi is inflaton, the sigma is a scalar field with continuous spectrum. And then,
So do you need to impose some kind of symmetry to guarantee sigma has a continuous spectrum?
symmetry, I don't assume anything at this point. Yeah, and also in data. This is just a kind of example.
So why do you take f sigma in front of the inflaton kinetic term? You cannot take just one?
You mean the f equal to 1? At least we need a coupling to get because we want to concentration sigma decay to the influx.
Yeah, it's okay. Another way, why do you assume sigma and pi couple only through this kinetic term rather than the potential?
Actually, it's not necessary. This is just you can also get similar result even if you assume some mixing there. But actually, this is a kind of famous setup for the quasi-single field inflation.
What?
The so-called quasi-single field inflation. So
Sorry.
this is the how to say the first model for the cosmological collider.
Oh, okay.
So I use this setup. I want to extend that model so that it contains a continuous vector. So no reason much. But later, actually, this produces many interaction, and I choose some specific coupling. There, I have a reason because I need to calculate. I want to calculate everything analytically, so I choose some specific interaction. But this setup doesn't have much meaning. Okay, so quantization, the inflaton is the same. This is a quantization for the massless field, almost massless field. And for the sigma field, apart from the usual case, I included some spectral density effect. So we essentially have the integral of the spectral density here. And yeah, I follow these works, and they are discussing some effect of the dark matter phenomenology. Okay, so as I mentioned, that setup, that Lagrange produces many interactions if you expand around the inflation background. And I focus on this kind of two interactions. Of course, you have more and you can make a more complicated diagram. But if I assume this is dominant, then you get this kind of diagram. So this is a simple diagram, and sigma particle created and decayed to the inflaton fluctuation. But I stress this particle has a continuous spectrum. So what yeah.
So here A is the scale factor in the FRW.
I'm sorry, I didn't explain. This is a scale factor, and this is a F in the setup. I mean the kinetic coefficient of the. Let me go back. This F, and F sigma is the derivative of the
round F round sigma.
Yeah, round F round sigma, and phi 0 is the inflaton background, and the delta sigma delta phi is the fluctuation.
So in the second line, you don't multiply delta phi the scale by any A term, but the second term in the it is multiplied by 1 over A scale. So how this scaling?
This one?
Yeah. The
because
first one and the second one, they have a different dependence on the.
Oh, right. Because this is we are thinking now the FRW metric. So 1 is square scale, right? Metric is 1.
In the conformal
then this depend actually derivative and time derivative and special derivative are equally true.
Yeah.
But this is a usual time.
Okay.
Yeah.
So the second derivative del contains both time and the space derivative.
This one is just a space-time derivative.
Space-time.
No, sorry, space derivative.
Only space.
Spatial derivative.
Only space.
Yeah, only space.
Okay.
Yeah. So if you go to the conformal metric, then yeah, maybe you can factorize this one. Okay, so we are interested in the 3-point correlation function of the inflaton, and yeah, these are evaluated in the momentum space. We have 3 momentum like K1, K2, K3, and especially in the cosmological collider, we are interested in the so-called squeeze limit. That is the 2 momentum that are much larger than the one here, K3. So I parameterize the ratio of the large momentum to the small one as a kappa, and you can find in this limit this 3-point correlation function can be calculated analytically. And before going to our result, let me remind you the usual case. This is a single particle with a definite mass. In this case, as I mentioned, this F is here. This F is given by this expression. So the important point is with respect to the kappa, we have oscillation because sine to the kappa, and also this frequency is determined by the mass of the sigma particle. And we have a Boltzmann suppression factor in general. And here A and phi is a very complicated function of the mass of the sigma particle. But you can calculate it analytically in this limit.
So what determines this scale of log, argument of log? Kappa is dimensionless. Yeah.
Dimensionless, yeah.
So kappa really means k over what?
This is the definition of kappa.
Ah,
Sorry.
sorry,
We have
yeah,
three
yeah,
momentum,
yeah.
so the ratio, yeah. Also, yeah, you can naively expect in the continuous case, they're almost the same, but just you get some integration of the mass with the spectral density this way. So I don't think I don't need to explain more, but yeah, the pink box is the only the difference. So this is the kind of main result. So I want to draw a figure, but without specifying the spectral density, I cannot write the figure. So I choose a specific spectral density, which is a kind of polynomial as a function of n. And yeah, again, I say this kind of function is used for the matter phenomenology by these guys. And also, this is the result. These are the almost the same figure. Only this M0 parameter is different, and the y-axis is the f. F is same as the three-point correlation function, roughly speaking, and the x-axis is the kappa. And maybe you can see this gray line is the normal situation with I mean the single particle with a definite mass. The gray line is a prediction of the single particle. But in the continuous case, which is denoted by the red one, you can see some damping amplitude in the squeezed limit. And this feature is, you can see the similar feature even if you change some parameter. So damping amplitude, we can say damping amplitude can be a signal of such continuous spectrum. And also, this is not physical explanation, but technically, so we have a integration of the mass spectrum. So you get some 1 over kappa factor after the integration. So this damping amplitude is a kind of consequence of the integration. So actually, up to here, this is a story of the continuous spectrum, and also I want to introduce my recent work for the time dependent mass. But so far, if you have any question.
Show me the how it looks like the spectral function.
This one?
Yeah.
Yeah,
that one.
Yeah, that one is the.
I mean, let's say, for example, do you have any plot for that as a function of that?
What's the shape?
Shape, yeah.
Shape, actually, this is quite similar for the. This one. Starting from M0 called gap scale. Before the, how to say, the lower value compared to M0, you don't have low M is a 0, but at some gap scale, it's grows like just following a square root function.
Then I don't know, maybe I'm confusing, but spectral, the integrate over the whole mass of spectral density should be 1. Is it true?
Yes, but in my case, this maybe you can see. I didn't show any equation, but okay. First, suppose a normal situation. You get you can if you calculate the three-point correlation function, it depends on the mass, right?
Yeah.
Mass of the sigma particle. Then this factor is multiplied. So integral of this one maybe gives the 1, but this times some complicated function of the mass.
I just wondered that type of function gives a 1. If it's monotonically increase then.
Okay. Okay, maybe I was wrong. It's not necessary to be one, right? Because if you discretize the spectrum, this is just a multi-field effect, right? The summing up the mass, not necessarily, the summation not necessarily to be one, right? Can be infinite, no? Then why we get a finite, finite result is because the correlation function contains some Boltzmann separation factor. So we sum up from M0 to the infinity, but the infinity we get a damping because of the Boltzmann separation. So we get a finite result. Yeah, but the integration of the spectral density itself should be not necessarily to be finite, I guess. Maybe I said wrong. Does it make sense?
Could you show the next slide? Yeah.
Here.
So del sigma up to so consider delta phi, delta sigma, delta phi, delta phi.
So delta.
So
You mean 4.1?
Yeah, 4.5. Yeah. With the delta sigma in the intermediate state. And does it the unitarity violated or not in your scenario?
Maybe I want to make sure your point. You're thinking the scattering of sigma to the phi?
I mean, from this the second Lagrange one, you have del sigma, del phi, del phi.
Mm-hmm.
So basically, you can have and the delta sigma is heavy.
Yeah, right.
Del phi is not.
Mm-hmm.
So delta phi goes to delta sigma and again delta phi, delta phi.
Okay.
And basically,
Yeah, right.
very typical scattering in the linear schedule in the Fourier phase. But in your case, your interaction is a derivative interaction. So I mean, it will blow up in the high energy scale anyway. So I think at a certain scale, there could be unitary vibration, but I wonder if you studied this effect or is it? I mean,
actually, maybe you can answer, right? I know.
Supposed by Boltzmann factor?
I know there's a one paper by Shiro. He discussed unitarity issue in this kind of scattering or non-Gaussianity. In this case, yeah, I think it should also apply. But actually, in my work, I'm not so interested in the magnitude of this guys because, as I mentioned, this cannot give a dominant contribution to the non-Gaussianity. I mean, more complicated diagram can be a dominant contribution to the total non-Gaussianity. So why I choose this diagram is just a calculability and also to catch some feature of the continuous spectrum. So if I need to discuss the magnitude, maybe we need to care about this size of the coupling. But yeah, I agree. In general, you can apply the unitarity discussion to this kind of in calculation.
So are you saying that this is not the main source of the non-Gaussianity?
Actually, it depends on the model. I don't specify the potential, right? But
potential F sigma or the scalar potential?
Yes, actually, it depends on the scalar potential. Actually, in the original model, they potentially include this kind of coupling. So then you get this is the original quasi-single field inflation model. They also claim this can be large. So, but in this case, the diagram is a little bit complicated. I cannot obtain the analytic expression. So I choose this simplest diagram instead. And also the unitarity discussion, the Cyril's paper, yeah, studying this kind of diagram. Yeah.
I have one more question. So that sigma can be, I mean, the largeness of the sigma can be decayed to the lower mass state during propagating, right?
Mm-hmm.
Such a case is discussing this here or not?
Maybe my situation, actually, I prepare a single sigma and suppose it's containing continuous spectrum, right?
I think in that case should be one, but
yeah.
Yeah.
But to discuss your point, we need to assume we prepare several particles, much field with a discrete mass. And we also need to consider the interaction between these guys, right? Sigma 1 to sigma 2, something like that. But in this case, I think it doesn't contain such a process between sigma 1 and sigma 2, maybe. This is my, understanding. Maybe this is just simply corresponds to the discrete one without interaction between sigma 1 and sigma 2, for example. Let me think more about that.
Okay.
But thank you.
So here you just ignore all the potential.
Potential terms. Yeah, actually, potential produce many interactions, but I just pick up the mass term from the potential term. I ignore other interaction coming from the potential. This is again just percentage.
So your formula here applies only in the squeezed limit?
Yeah. Actually, at this time, I didn't know how to calculate everything, but now I can. Actually, yeah, I remember. Identity gives a seminar, a lecture right here.
Yeah.
At that time, I'm interested in how to calculate everything exactly, and I study a lot. Then I understand this kind of diagram can be computed exactly using some technique. But when I wrote this paper, I didn't know about the technique, so I only showed the exact result in the squeeze ring.
So the function f of sigma, you explicitly give some function structure.
In this work, I didn't specify. Just need to depends. Sorry. Need to at least depends on the linearly. But if you do not, unless it's constant, you get this kind of interaction. Quickly explain this topic, the time-dependent mass. Sorry. So this is my recent work with Umiya, Toshumi, Masahide. And also, this is the setup. In general, inflation background gives a time dependence to a sigma mass. Yeah, so far I assume the sigma mass is a constant. But if you have this kind of coupling to the sigma and the inflaton, the effective mass is given by the summation of the bare mass plus the contribution coming from this coupling. So in this case, phi is an inflaton background, so you get some time dependence, or it turns out we get a scale dependence coming from this factor. So we are interested in the effect on the CC signal. And so far, actually there are work, but this is quite difficult, you know. So even for the constant mass, it's difficult to get the expression for the non-Gaussianity. But if once you change the mass, it's more difficult. So only the this kind of studies is done by only numerically. But I realized under certain assumption, we can get some analytical expression. And also another possibility to get a time-dependent mass is like a non-minimal coupling to the sigma, or of course you can consider derivative coupling to the sigma. But you can show this kind of time dependency is smaller than this kind of non-derivative couplings. So basically, I'm interested in this kind of shift-making interaction. Okay, so this is the analytic approach. I approximate time dependence of phi0 like this. This is just a Taylor expansion with respect to the conformal time. And I take a linear approximation of the inflaton field. Then you get the effective mass. You can also expand the effective mass in this way. So we realize that until this, up to this approximation, we can get the exact expression of the mode function of sigma. So here is the solution, and here W is the Hoitaka function. That is a special function. And the point is the time dependence, how to say, our key parameter is the kappa. Kappa is the kind of a derivative of the G function. So if the there is no coupling between inflaton to the sigma, this kappa goes to 0, and it's recovered to the constant situation. So I realized that based on the mode function I could derive, we can get fully analytical result for the 3-point correlation function with time independence included. Actually, you don't have to see the equation, but what I want to claim is that everything can be done analytically. No, this is no expression for the squeeze ring containing everything, every background, not only signal, and you can take any parameter. And also you can see there are some kappa in everywhere, and these are expressing the effect of the time dependence. And here's the kind of main result. Although this is preliminary, I assume just for simplicity, just the linear coupling between inflaton and sigma square. And in this case, alpha parameter is a key parameter. So our kappa is proportional to the alpha. So alpha, if alpha goes to 0, you get a constant. And also this is the so-called shape function, which is, roughly speaking, the 3-point correlation function I calculated. And this blue line shows the alpha equals 0. That is the corresponding to the constant concentration. But if you increase the value of alpha, you get kind of suppression in the squeeze rate. Here, X is like a kappa in my previous slide. So if you go to the squeeze limit, K3 goes to 0, then you get a large 1 over X. So this direction corresponds to the deep squeeze limit. Oppositely, if you decrease or increase negatively the parameter alpha, you get the enhancement of the spectrum. Here, blue one is the constant mass, and these two lines shows the time-dependent situation. So this alpha, you see, if alpha is a positive, you get the increasement of the mass of sigma square. But if alpha is negative, as phi evolves, you get the you get the small mass of the sigma becomes small as phi evolves. So what we found is a large deviation from the standard constant, the constant mass situation, and this can be existence of time dependence. So this is a final slide. I want to think about why this kind of deviation occur. So in the squeeze limit, that is you remember the triangle, right? Squeeze limit corresponds to one of the momentum is much smaller than the others. In this case, squeeze limit means the correlation between the long mode K3 and the short ones K1, K2. Actually, long mode K3 exits the horizon at the early times before these short one leaves the horizon. So you can easily calculate the super horizon evolution of this long mode, which corresponds to K3. And you can estimate the mode function of the long mode at the late time, like this. Then you get this mode function is suppressed or enhanced by this kind of Boltzmann suppression factor. So in my case, when alpha is positive, the mass of the sigma increase. So you get the much suppression by this factor. But if alpha is negative, this changes the sign, so you get the enhancement of the sigma. So this is a kind of physical interpretation of the result.
V is the mode function of the massive field or
Massive field, sigma.
Okay, that's confusing. So this massive field decay before cross the horizon or not?
Massive field decay just after the horizon crossing.
Just after the horizon crossing.
Horizon crossing point is a kind of boundary.
Then one is this is the superhorizon evolution of the massive field after horizon crossing, right?
Yeah, right. So it's decay. Yeah, of course, as you say, it contains decaying factor.
Okay.
But in our case, mass itself has a time dependence.
Right.
So essentially, Boltzmann suppression factor has a time dependence, and it evolves after the super horizon, after the horizon. Depending on the alpha, it becomes heavier or lighter. But this is expressing such a thing. Normally, if you have a constant situation, this doesn't exist because it's just a constant. It doesn't evolve. But in our case, after the horizon exit, it evolves. So the mode function feels lighter mass or heavier mass, something like that.
Let me.
Okay, thank you. Let me finish. Let me summarize. Yes, thank you for listening. I want to say is the cosmological collider is a new attractive tool for the exploring high energy. Although we have many things to be, we need, for example, more precise evaluation. Still many things to do. But today, I focus on the continuous spectrum on cosmological collider. As I mentioned, getting the Fourier analytic expression is very difficult, but even under the approximation, this kind of specific spectrum gives some specific signal to the cosmological collider. For example, in the continuous case, we have a damping effect in the squeezed limit. And also I choose the specific form of the spectral density, but even if I change the spectral density as a as a polynomial function, I didn't see any difference. So maybe this kind of feature is quite common in the continuous situation. And also point is that this kind of signal cannot be mimicked by the usual situation. So we can say it can be a strong evidence for the continuous spectrum. And also, I haven't studied much about UV embedding, but now I found a good paper by Sandram. So I think it's interesting to think about more complete UV embedding. And also, in the second part, I discussed the time-dependent mass. And this kind of time dependence is kind of quite general because if you couple inflaton to the sigma field, that inflaton gives time dependence of the sigma field. And also we found some analytical estimation under the linear approximation of the time dependence. And we found the amplitude enhancement and suppression, and also change of the wavelengths in the squeeze limit. And also this is again the large deviation from the standard case, and can be a nice feature of this kind of time-dependent situation. Okay, thank you very much.
Thank you very much for the info. Question?
So what you are calculating is, how do you observe what you are calculating from the 3-point population CMB spectrum?
Yeah, it's I don't know much about observation, but this is first of all for the magnitude we have many constraints from the Planck data. Actually, it depends on the form of the triangle, but roughly speaking, order 10 or like a 50 or something, that we have some constraint for now. So very, very large size of the non-Gaussianity is already excluded. And also in the future, we have some other experiment like 21 centimeter observation or something. And optimistically, we hope more stringent restriction on the non-Gaussianity. So people say like 0.1 or order of the 0.1 FNL can be observed in the future. So
when you speak about some correlation function of the dimensionless quantity, I mean, so what should be the proper dimension you should make this delta phi dimensionless? I mean, in principle, delta phi, naively, delta phi dimension is 1, mass dimension 1. But here you are really scaling. Basically, you are talking about dimensionless delta phi. Is that right?
Actually,
or do you normalize the 3-point function by 2-point function somehow?
Actually, in my talk, I don't distinguish the correlation function of the delta phi and the curvature perturbation. But so in the precisely speaking, delta phi has a dimension, but the curvature perturbation has a dimensionless. Yeah.
So when you say, I mean, expect, for example, order 1 non-Gaussian.
And T means not the delta phi, the correlation function of the curvature perturbation. Yeah, dimensionless. Yeah. So yeah, right.
I have a question. So in your second case, did you also consider the background dynamics. I mean, from that, the couplings, it's the background dynamics good or not?
Background dynamics, I approximate the background of phi by this kind of Taylor expansion.
Yeah, but in principle, you have to solve the background.
Yeah.
The equation motion to
Exactly. In this case, the discussion becomes model dependent. So,
I mean, but you have model.
actually, I don't specify any potential or any Lagrange, just assume the coupling between the inflaton and the sigma, like G phi, and then I include the time dependence of the inflaton by this parameterization. In that sense, I don't solve the equation motion.
Right.
But even if, how to say? Yeah, I agree. We need to solve the equation motion. But no matter how it's formed, but you can expand in this way, right?
That's true, but that the coupling, what you assume, might spoil it.
Yeah, exactly. Yeah, that's a very good point. Yeah, actually, in general, the G phi coupling also affecting kind of back reaction to the inflaton.
Yeah.
So yes, exactly, and also in the figure, I take a linear coupling that may gives us some big effect on the inflaton potential. So in that sense, we need to consider some back reaction effect. But in this case, I just, how to say, ideally assume there exists, maybe for the quantum correction, maybe, I don't know, we can assume supersymmetry or some discrete symmetry, which may help. For the classical dynamics, it's quite model dependent.
I see. Any other question? Okay, now let's answer.